Thank you very much, Lisa. So yes, so in fact there's going to be two parts to what I'll do. I'm going to give you a taster lecture on pure mathematics, and then I'm going to say a little bit about the maths courses at the University of Nottingham afterwards. Right, so we'll start with the taster lecture on pure mathematics. I am Joel Feinstein. I'll tell you a bit more about myself in a moment. I've got a blog at explainingmaths.wordpress.com, where you can find out all about my ideas about how to try and explain maths to students, well, anyone really. Right, so who am I? I'm an associate professor. I work on pure mathematics, and I'm also the outreach officer in the School of Mathematical Sciences. So I actually organise events like this one and other community taster events and things to try and explain mathematics to people. I'm also the teaching support officer this year, which means that I help the first year mathematicians, when they come in, start their course with the core modules, which is about half of the first year. I have drop-in sessions and people can ask me questions at any time, really. And I also teach the introductory pure maths module, the first one that people see at the beginning of the first year of the degree. And I'll tell you a bit more about that later as well. My research work is on Swiss cheeses, well, and actually it's in functional analysis, but one of the things I specialise in is Swiss cheeses, which are these strange shapes which you get by taking a disc and punching out infinitely many holes, each of which is disc shaped, and you get these peculiar shapes like this, which if you choose the holes carefully, you get all sorts of weird properties, but I won't be going into that today. So this taster session, it's based on part of the first lecture from my first year module, Foundations of Pure Mathematics, which I'll call FPM for short. And you can find several complete sets of videos by now. I don't recommend you to watch several complete sets of videos, but you should be able to find some. You can find some on YouTube. If you follow this link, it'll take you to a page which links to various different versions of the Pure Maths videos. And I'm going to be asking you some questions today, so you get a chance to participate. And here is a URL. There'll also be a URL in the chat, which you can find. It says to participate in the interactive activities today. Here's the link you can use on your mobile device or whatever machine you're using. Yes, so in fact, I do this throughout my teaching. I always make sure to have some interactive questions, and it gives me a chance to see how well people are understanding what I'm saying, and it also gives people to have a chance to find out how well they understand, and it gives people a chance to try and convince their neighbours that they've got it right, which is actually one of the best ways to learn maths, is to try and explain it or convince someone else. So I'm going to start you off with this question. So here's the first question I'm going to ask you, and you can vote on this whenever you like using the link in the chat. And the question is 1 a prime number? But the point I want to make in asking this question, because you've probably been told yes or no, is how important it is to know definitions when you're studying mathematics. Because if you don't have a precise definition for the concept you're working with, then it's very difficult to know whether you've got the answer right or not. In fact, the answer usually depends on whether you're working with the correct definition. And so, I mean, maths is full of asking questions about things. And if you're not quite sure what the thing is, it makes it very difficult to answer the question. Okay, so what I'll do is I'll just let you give you a little bit longer to say whether you think 1's a prime number or not, and then I will show you what you've come up with. and then I'll explain what the issues are and why it's important to have a clear definition of a prime number. So I'll just give it a little while longer. So far, everybody's voting for the same thing, so it does look like you've all been told whether or not one is a prime number or not. But if you've already answered, you might think about why do you think your answer is correct? Have you been given a formal definition? Are you absolutely sure that your answer is right? Okay, let's see what people have gone for. So I've got 7 answers, and most people have gone for B, but we do have at least one person going for A. So let's just remind ourselves what those meant. So most of you think that 1 isn't a prime number. One of you's gone for 1 is a prime number. And I think it's perfectly reasonable to think either way if you're not entirely sure of which definition you're working with. But okay, let me tick the no, because that's officially the correct answer. But I'm going to give you a definition in a moment, and once I've given you a definition, that will, of course, tell you whether or not 1's a prime number as part of the definition. But what you might be wondering is, I mean, you know, prime numbers got something to do with, is it divisible by anything interesting, or is it only divisible by itself and 1? And then you think about 1 and you think, well, that's only divisible by 1. And so maybe 1 should be a prime number. But mathematicians don't want 1 to be a prime number. And there's a very good reason for this. In fact, lots of very good reasons for this. One of the reasons we don't want 1 to be a prime number is when you factorize positive integers as products of primes, like 1,000, which you can write as 2 times 2 times 2 times 5 times 5 times 5, writes it as 2 cubed times 5 cubed. That's essentially unique. There's not really any other way of writing 1,000 as a product of primes, except you could change the orders of the 2's and the 5's when you're factorizing it. But if you threw 1 in as a prime, then you could choose to multiply by 1 or by 1 squared or by 1 cubed or whatever. It wouldn't be unique at all. And that's just one of hundreds of results where you'd have to say, well, this works for all primes except 1. So ignore 1. It's much better if you say, no, 1 doesn't count as prime. So you don't have to keep saying except 1, because 1 just isn't as good as the other primes from this point of view. There are other things, 2 is also special because 2 is the only even prime number. And so sometimes you have to say for all odd primes, and sometimes you really have to do that. But anyway, so that's one reason why it's important not to call 1 a prime number. But what I said is that we need to know some definitions in order to be able to decide whether things are true or not. So let's have a definition. Now, first, I've got to remind you what integers are, and that's just basically whole numbers, positive, negative, or 0. So I'll write that down first. So integers are whole numbers, which could be positive, negative, or 0. Oops, or 0. Try again. So you've got all the non-negative ones, but you've also got the negative ones. So those are the integers. And a prime number is an integer p with p, I'll just say with p greater or equal to 2, because that'll rule 1 out straight away, such that so that p isn't divisible by any other positive integers except for 1 and p. So p is not divisible by any positive integers except for 1 and p. What's this word positive doing in there? Well, I want to make sure, I'm dealing with integers, and sometimes I might be dealing with negative integers. And you might wonder, is 2 divisible by -2? I don't want to get into that, so I'm just going to talk about whether you're divisible by positive integers. But notice that you can divide 2 by -2 and you'll get -1. And that's an integer. So if you do start dividing by negative integers, you've got a few more cases to worry about. Okay, so now we know what a prime number is. I can give you another question. I'm going to ask you 2 questions about prime numbers. Let's start with problem 2. How many prime numbers p are there with the property that the square root of p plus 1 is an integer? This is the non-negative square root. Because mathematicians, when they write square root, that's a non-negative square root. Now, you shouldn't find this obvious at all. But what you can do is try a few prime numbers out and see if you find any. Then try and make a guess as to what you think the answer is. And then, once you've got a guess, see if you can think of a reason. Because, you see, this one, well, I'll tell you more about the problem in a minute, but let me give you, don't vote yet, because I need to just get rid of all the previous responses. Okay, you can vote anytime now, but I'm going to give you about a minute and a half to think about this one. Try to figure out what the answer is and see if you can prove it, because proof is another stage again. So are you absolutely sure about your answer, or are you just guessing? Give you a bit more time on that one. And if you've got anybody with you, try to convince them that you're right. Because best way to learn maths and understand maths is to explain it to someone else. Which is one of the things that our past leaders find out in Nottingham, our peer-assisted study system, where our second, third and fourth years, some of them will help the first years with the difficult concepts in first year mathematics. And in the process, our past leaders also learn quite a lot themselves and really solidify their understanding of everything they're explaining to everyone else. So I think it's good for everyone. Right, let's have a look. Oh, I've only got one reply so far, at least. There is a bit of lag, so you're probably about 20 or 30 seconds behind me. Now some answers are coming in, and we're getting quite a lot of different answers. So that's good. Just give you a little bit longer, because I've only got 5 answers so far on my display. Right, let's see what people have come up with. Okay, so it looks like most of you have gone for C, with some people for A, some people for D. Oh, all sorts are coming in now, right? So lots of different possibilities. Let me tell you that the correct answer to this one is C. There's only one prime number, P, so the square root of P plus 1 is an integer. And the majority of you have got that right. Whether it's a guess or a proof is not clear. At this point, in a normal lecture, I would invite someone to be brave enough to explain why they think there's only one. But I think I won't do that today. So what I'm going to do is I'll say something about this straight away. But if you figured out a proof that there's only one, you should be very pleased with yourselves, because that's a really good example of mathematical reasoning of the kind that you need to do in pure mathematics at the University of Nottingham. Okay, so let's say something about this. First of all, which prime is it? Well, I think probably most of you will have found that 3 works. So notice 3 is prime, and the square root of 3 plus 1 is the square root of 4, which is 2. Remember, it's a non-negative square root, so 3 works. That's a good start. We found at least one. And then you try 5 and it doesn't work, and 7 doesn't work. And then hopefully you don't try 9, because 9 is not prime. And then you try 11. Oh, of course, 2 didn't work either. You probably tried that. And 11 doesn't work. And then you keep trying more and more. And you try 100 primes and none of them seem to work. And then you try 1,000,000 primes and none of them seem to work. But it doesn't help, because no matter how many you try, the next one might work unless you've got a reason why it can't. And there have been conjectures in mathematics that have been true for the first billion numbers, and then someone's found a counterexample, but it's much bigger than 1 billion. So just because you've tried 1 billion cases doesn't mean that you know what the answer is. You've only got a good guess, unless you find a proof. So I said that I was going to talk about definitions, proofs, and examples. Well, I talked about definitions already. Now we're talking about proofs. How can we be really sure that there's only one prime that works? Well, I'm going to give you a proof. If you thought of a proof yourself, well done. Okay, so there'll be some mathematical language in this, which is what we always put around. But the main idea, it's about factorization. So let's suppose that P is a prime number, and that square root of P plus 1, non-negative square root, is some integer say we'll call that K. So K is an integer, and the square root of P plus 1 is equal to K. We know a bit more. P's a prime number, so P's at least 2. The P plus 1's at least 3. We've taken a non-negative square root, so this is at least a square root of 3, and that's bigger than 1. So notice K is actually definitely bigger than 1. Since P is greater than or equal to 2, that's part of our definition of being prime, remember. Since P is greater than or equal to 2, the square root of P plus 1 is at least the square root of 3. Remember, it's the non-negative square root, which is greater than 1. So K must be at least 2, because it's an integer. That might be helpful. Okay, so that's just a little bit of information. If you can do this, the integer you get's got to be at least 2. And in fact, of course, we know you can get 2, because if you take P equals 3, then you get square root of 4, which is 2. So 2 is possible as well, but it's got to be at least 2. Okay, so we've got this information. Square root of P plus 1 is equal to K. And K is an integer. That's at least 2. Let's square both sides. We get P plus 1 is equal to K squared. And so P is equal to K squared minus 1. P is a prime, it's equal to K squared minus 1. Now that might look suspicious to some of you, because K squared minus 1 could be factorized as K plus 1 times K minus 1. And so these two numbers divide p. P is divisible by these two, but p is a prime number. There aren't many things that divide prime numbers. Prime numbers can be divisible by p, by 1, and maybe minus p and minus 1. But notice k is at least 2, so there's no negative numbers here. These are positive. So we're not talking about minus p or minus 1. We must be talking about p and 1. And obviously, it's got to be k plus 1 that's p and k minus 1 that's 1. Since p is prime, the only positive integers that divide p are p and 1, or 1 and p. So if I move up here, so we must have well, these two divide p because you multiply them together to get p. So one of them must be p and the other one must be 1. And it's obvious that it's a bigger one that's p. So we must have p plus 1, k plus 1 equals p. Can't have p plus 1 equals p. So we'll have k plus 1 equals p. And k minus 1 equals 1. K minus 1 equals 1. So k is 2 and p is 3. And I'll do a little square to show I finished the proof, because that tells you that if this happens, p has to be 3. And that's how you do that one. Right. Okay. So we've solved a question about prime numbers. I'm going to give you another one to think about. Don't vote on this one yet. Let me, you start thinking about it and I'll tell you when you can vote, but don't start voting yet because I've got to zero the answers. Okay, I'm ready. You can vote at any time on this one, but you may have to think about it a bit. Do you think you can prove your answer? Do you have a guess? You can vote any time now. Got no answers yet, at least. As I say, there's a bit of lag, so you may have already answered by the time you hear this. But I can't see any answers yet. Okay, well, I've got my first answer. Well, if you haven't voted yet, maybe you can. I expect the answer, maybe a few more will come in, but let me show you what I've seen so far, which is, oh, 2 responses now. There we go. So 2 answers so far, and you've both gone for B. And maybe some more answers will be trickling in a minute. But anyway, so B, infinitely many. Well, that's probably right. Okay. I'll put a question mark on that because it's probably right. But the real answer here is no one knows yet. Okay. So A and B could both be right here. I asked you to choose one answer, but in fact, the one that's known is that no one knows yet. This is one of Landau's problems. It's a problem that nobody even knows how to try to solve this one. Note, all I did was change p plus 1 into p minus 1, and Yeah, I can see an interesting question there, which I might. Somebody is asking about the number 0, and 0 is indeed divisible by every single number you can think of, except possibly 0. So if I'm sticking to dividing by positive integers, 0 is divisible by everything, and that's very special. But of course, it certainly doesn't count as a prime number. So how do you describe it? I mean, it's what's called an additive neutral element, 0, and multiplicatively it's, well, a 0 element. It swallows everything. If you multiply 0 by anything, you get 0. So it's got two very different roles for addition and for multiplication. Addition, it doesn't change anything, and for multiplication, it basically changes everything into itself. So 0 is a very special thing, but we call it the 0 element of your algebraic structure, whatever it is. So I think that how would you describe it is as a 0, probably, and I'm not sure about another way of describing it. Right. So where was I? Yes. Nobody knows the answer to this one, and nobody even knows how to begin about going to solve it. Whereas the one before we solved with elementary argument, this one, well, what happens is this time, instead of just finding one you can't find anymore, this time you keep finding more and more and more, and wherever you look, you keep finding more. But how do you know that you're going to keep finding more? So this time, as you go up to 1 billion, you keep finding more and more. How do you know that there's another one? But of course, you look further and you do find another one, but because people have checked a long way and they keep finding more and more, but nobody knows if they go on forever. They're pretty sure it's likely. It's one of these things like a bit like something called Goldbach's conjecture. It's one of these ones where people are almost sure of what the answer is going to be, but if you can't prove it, you're not sure. So nobody's absolutely sure because there's no proof. Look up Landau's problems on the web and you'll get more information about this. It's quite fascinating. You might wonder, why do we care about prime numbers and all this stuff? Of course, a few hundred years ago, or even going right back to Euclid, I suppose, thousands of years ago, but certainly a few hundred years ago, people were doing a lot of work on prime numbers and number theory, and nobody thought it was important for anything. It was just good fun, really interesting, proving lots of mathematical results about prime numbers, and everybody thought this was just a really interesting and difficult game, if you like, to play around with prime numbers. Nowadays, encryption systems completely depend on what you do with prime numbers and the theory of that. And so what used to be just fun is now completely crucial for the safety of your money online when you're doing shopping or internet banking or anything like that. So it may have been that prime numbers weren't important once or weren't known to be important, but they're extremely important now. So if you go online and look up encryption systems, you'll find it's full of number theory and prime numbers and things like that. And that's something you can learn a lot about if you come to university. So yes, you can learn about the number theory and the prime numbers, and you can learn that just for fun, or you can learn about cryptography and coding cryptography and that sort of thing. And you can learn out how to apply it all in order to develop really good encryption algorithms. It is very important that the good people stay ahead of the bad people here, because if criminal masterminds become too good at number theory, they might figure out how to crack the encryption algorithms, and then your money won't be safe anymore. But at the moment, the good mathematicians are winning, and nobody can crack the encryption algorithms at the moment. So you seem to be all right. Keep an eye on the news. If they say quantum computers now solve your encryption algorithms, your money is no longer safe, then beware. Okay, right. So now I want to finish today when I say finish today, finish this taster lecture portion by talking about something called Simpsons Paradox. And like most paradoxes in mathematics, it's not really a paradox. It's just an apparent paradox. It's something which appears to be impossible, but is actually true. So I'm not going to spend too long on this since we've been going quite a while now. But it's a competition, this one, between two vets. But actually, if you look up Simpsons Paradox on, say, Wikipedia, you'll find loads of real world examples where this sort of thing happens. Okay, so it's two vets and they're competing, vet A and vet B, and they claim to be better at treating a certain animal disease. And vet A says, we're better because we cured a greater percentage of our male patients than you did, and we cured a greater percentage of our female patients last year than you did. Vet B says, well, that may be true, but we cured a greater percentage of all of our patients than you did last year. So I want you to have a think about that. And there's no tricks here. These animals are either male or female. And the numbers are not zero. None of the numbers are zero. So there's no tricks. And I want you to think, does this seem even possible, or must one of the hospitals have got it wrong? Could it be that one vet is better at treating male patients and better at treating female patients, but the other vet is better at treating their patients? I'll just give you a while to scribble on the back of your envelope to see if you can figure out any examples. Remember, if you want to find an example where this happens, you've got to find 4 numbers for each vet. You've got to decide how many male and female animals they each treated and the number of each type that they cured. So I'll just give you a little bit longer and then I will reveal the answer, or an answer. Okay, so I'm going to give you an example where this can happen. When I was first told about this, I said, that can't possibly happen. I'm sure I can prove that can't possibly happen. There's no way that one of them can be better at treating male patients and better at treating female patients, and yet the other one's better at treating their patients. It just doesn't add up. It's not fair. And I tried to prove it was unreasonable. And since some people said it could happen, I had to bear in mind the possibility that maybe it could happen. And remember I said I was going to talk about definitions, proofs, and examples. If you can't prove something doesn't happen, that might be because of an example where it does happen. And of course, when you find an example, that is also convincing. So here you are. In this table, percentages have been rounded to the nearest integer, but if you work them out exactly, you'll find I didn't cheat. The rounding hasn't actually done anything to do any damage to this. So, vet A, 10 male patients and cured them all, 100%. Fantastic. You can't do better than that. Vet B, 90 male patients, but only cured 89 of them, which is basically a pathetic roughly 99% cure, nothing like as good as 100%, right? And then for the female patients, vet A, 90 patients cured 56%, that doesn't seem to be so good, but vet B had 10 female patients and only cured 3 of them. That's only 30%, miles worse than vet A. So vet A's better at the male patients and better at the female patients. But let's have a look at the figures for all patients. Vet A, 10 male patients, 90 female patients, that's 100 patients. And the total cured, 60, about 60%, right? Vet B, 90 male patients, 10 female patients, that's 100 patients again, but they cured 92% cured. Miles better than vet A. So yeah, vet A is better at curing its male patients and better at curing its female patients, but vet B is better at curing its patients. Well, there's usually an underlying reason for something like this. I don't know what it is. I would be asking some questions of these vets. Why are so many female? Why is it such an imbalance in the number of male patients and female patients going to each? And why are they both so bad at curing their female animal patients? And that doesn't seem right either. So if you it's quite often an underlying reason, a hidden variable, some information you don't have when this phenomenon happens that explains what's going on. But I have to say, I can't tell you which of these two vets to take your animal to. I really don't know. Perhaps there doesn't seem to be much difference in the male patients. They seem to both be very good. The number of female animals doesn't seem to be very large here, so it's hard to be sure. Perhaps it looks pretty bad, though, that they only cured 3 of their 10 female animals. Anyway, I can't say much more about that, but if you look up Simpsons Paradox, you'll find there's loads of examples in real life where this sort of thing happens, and there's often a reason for it. But it's been done with average scores in cricket. It actually happened in a competition between 2 brothers who were trying to, and one of them had a better batting average over each leg, but the other one had a better batting average overall, something like that. And it wasn't quite clear who'd won their bet. Right. Okay, so here are some useful links. I'm going to make these slides available later. But here are some links. There's a link to the University of Nottingham's School of Mathematical Sciences and our maths courses. This one to University of Nottingham. This one is our links to our maths courses if you want to study with us. This is a link to the complete sets of videos from my module Foundations of Pure Mathematics. And there'll be a link in the chat where you can give a feedback on this session. But before we move to the Q&A, and please do give us feedback before you leave. I have to warn you that when we finish this session, when the event ends, the chat will disappear and you won't be able to get back to it. So if you can memorize that URL in case you want to give us feedback later, that'd be very good. Right, so I'm going to move on now to tell you something about the maths course at Nottingham. But if you do have questions,